Hello, everyone. Thank you for watching the talk. In this talk, I'm going to be talking about explicit abelian lifts and quantum LDPC codes. The joint work with Fernando, Ryan, Pedro, and Madhur. So the main goal of the work is to explicitly build symmetric expanding graphs. So in the talk, I'll try to motivate as to why this problem is worthy of study and how we construct such graphs. This beautiful image from the survey by Huri, Linear, and Wilderson is of the three regular infinite tree whose quotients give us expanding graphs. All right. So the outline of the talk is as follows. We'll introduce the problem and give some history of it. And then we'll state our results and show how they can be achieved to use quantum LDPC codes. I will not really talk about the proof or the proof sketch, but I would like to single out the key technical lemma that goes into the proof, which is a better count of a certain combinatorial object. And we'll then conclude with the summary and open problems. Okay, so let's get started. So expansion is one of the key graph properties that has been very useful in theoretical computer science. And it's a notion that captures how well connected a graph is, right? Formally, there are multiple notions of what this thing is, and we're going to look at the spectral definition. So let AG be the adjacency matrix of the graph. You can compute its eigenvalues, and here lambda2 is the second largest eigenvalue, and lambda n is the smallest eigenvalue, right? So define this quantity called lambda of G of a graph G, and the smaller the value is, the better you expand it, right? So for example, the complete graph, which is the best an expander can get, has lambda of Kn is 1. And the main task is, can we have sparser graphs, right? Like ideally constant degree graphs that achieve this. So if your graph is deregular and in the worst case is disconnected, then your lambda G is D. So this is like the worst possible it can be. And the question is how much smaller than D can you make this quantity? Now this captures the notion of random walks and how quickly random walks mix. So this image illustrates a simulation of a random walk, and in a well-connected, dense, well-connected graph, random walks should mix pretty quickly, right? So given D and epsilon, can you construct infinite families of deregular graphs, Gn? So here we want to think of n as a number of vertices of the graph, which goes to infinity. So you want an ever increasing family of graphs such that the spectrum, this eigenvalue is bounded, right? So the second largest eigenvalue is bounded away from D by the epsilon D, right? And here the key thing is you have the freedom to choose to construct these graphs once you give an epsilon, right? So you can make them very small. The best you can do, given by this bound by Alan Bopena, which says that ignoring vanishing factors with n, asymptotically the best you can do is 2 square root d minus 1. And graphs that achieve that are called Ramanujan graphs, and they are like the optimum expanders. Whereas when we say epsilon d, we're asking for a much more modest requirement, right? However, for applications, epsilon d more than suffices. So this is a good enough problem to tackle. All right. The other very interesting property the graphs have is symmetry, right? So formally, a graph isomorphism or an automorphism is a bijective map between the vertices such that every endpoints of an edge are mapped to endpoints of another edge, right? So if you have u and v are adjacent, then f of u and f of v are adjacent, and vice versa, right? So such maps are called isomorphisms or automorphisms. And if you collect the set of all such isomorphisms, they form a group under the group operation of composition, right? Composing two bijective maps is your bijective map, and moreover the property is satisfied. So this is a group of automorphisms, and the question is, given a group H, can you construct a graph such that H is a subgroup of this automorphism, right? Can you construct a graph G with this property? So let's take a simple example. Let's say the group is a cyclic group, right? Then there's a very natural graph that you can build. So let's say this the cycle graph on 6 elements, and this has Z6 as a subgroup of its automorphism group, because for every I in Z mod 6Z, so think of IS from 0 to 5, you can define an isomorphism that shifts the elements by I, right? That rotates the circle by I, and this gives you an isomorphism. All right. So we've seen two properties. So expansion. The question that I asked has been solved, and by now we know a lot of explicit constructions of constant degree expanders. Right. On the other hand, if you just ask for symmetry, we also know how to do this. So Babai in the 70s showed that for any finite group H, you can explicitly construct this graph whose automorphism group is exactly H, not just contained, right? And the existential result was known all the way back in 30s, right? So now what remains is to ask if you can get both, right? Why not get two nice things? And this is the focus of it. So why would you want to do it? There are multiple reasons. Let's look at two of them. The one that motivated us to look at this is the recent slew of results on constructions of quantum LDPC codes. So given two linear codes, C1 and C2, which have a symmetry of a certain group H, you can define a quantum CSS code out of it by taking the tensor product and doing some sort of a quotient operation on it that we won't get into. But the key thing is you need symmetry of the group. And this was defined originally by Hastings, Ha, and O'Donnell, and also shortly after, also used by Panteleev and Kalachev in the case when H is a cyclic group. So using this, they gave newer quantum codes that had a much better distance than its predecessors. And the work of Panteleev Kalachev, in fact, gives almost linear distance codes. Moreover, the recent breakthrough results of the new Evra, Livne, Lobotsky, and Moses on classical locally testable codes of constant distance and rate, and the work of Panteleev and Kalachev that give both classical locally testable codes as well as good quantum LDPC codes of linear distance and linear rate was can be seen as a construction of a similar construction where the group is no longer abelian, but it's this matrix group PSL2FQ of 2 by 2 matrices with determinant 1 modulo the scalars. All right. So in this work, it is crucial that the code is symmetric, and this code is in fact obtained by is a Tanner code. So it's like by the construction of Spitzer and Spielman. So you need an expanding graph. So you need an expanding graph with the symmetry of a group, which translates to the symmetry of the code, and the expansion translates to the nice distance properties. Right. Another application that I found really interesting was a recent paper by Goldreich and Victorson, which builds expander graphs such that the automorphism group is trivial. And then they use it to show certain lower bounds in property testing. So the key takeaway here is that it's nice to have expansion, but it's even better to have a control over its symmetries, right? And our formal problem statement, therefore, is that given a family of groups, Hn, can we explicitly construct a family of expander graphs, Gn, such that Hn is a subgroup of its automorphism, right? Here, the notion of explicitness that we work with is polynomial time in the size of the graph. So we're good with deterministic polynomial time algorithms in the size of the graph Gn. There are stronger notions of explicitness, and we do not work with them for the purposes of the talk, right? And notice here that we've relaxed the condition of Hn not being exactly equal, but just a subgroup. because this suffices for the application to quantum codes. Okay, so what are known techniques? So the Ramanujan, the most optimum Ramanujan graph for first construction using algebraic techniques that can be seen as Cayley graphs over certain groups like PSL2FQ. And these are indeed very symmetric graphs. However, this is not a generic technique. So you could not apply it for any group because the set of generators is constructed in a very specific way using number theory. So although these give great expanders with the optimum bound, we just know them for a specific set of groups, right? All right. So the most generic technique you could think of is via Cayley graph. So if you want symmetries of H, you might want to consider Cayley graphs over H over some generating set. And what Allen and Ruckman showed is that if you do not want to do number theory, then just take a random set, right? So just pick a random subset of size log n, where n is the size of your group, and you will get an expanding graph with high probability. The issue, of course, is that we aren't happy with log n. We want constant degree graphs. So this would mean that the degree is logarithmic, and that wouldn't work, for example, in the coding theory application, because the degree corresponds to the sparsity of the matrix, and for LDPC, you truly need constant degree graphs, right? And moreover, this bound is tight when the group is abelian, right? So of course, when the group is non-abelian, you have constant degree graphs, but when the group is abelian, like for example, the cyclic group that was used, like I mentioned in the earlier work on quantum codes, you cannot beat this, right? So this method isn't good enough for us. So we use the next very useful technique of lifting, which is again a very generic technique introduced in the context of graphs and construction of expanders by Abelian and Lineal. And you can look at it as a special case of a very generic and classical topological notion of covering maps, if you view the graph as a topological object, right? And this has been used a lot to construct expanders. So let's see what this operation is. So we define this a notion of lift called the HL lift of the graph, where you start with the base graph and you want to lift it to a larger graph called the G of S. And here L controls the amount of lift you want to do. So for every vertex, you replace it with L copies. So you have U1 all the way up to UL. Similarly, you have it for V. And now for each edge in your base graph, UV, you'll replace it with a perfect matching. And this matching or this permutation is given by the signing function S. So therefore, I denote the lifted graph as a function of this S. So this signing function maps an edge to a permutation. And so we want to think of this edge as a subgroup of the permutation. So when I say an edge shall lift, my permutation is to be in the subgroup. And then I just map I to S of E times I, where the permutation acts on the unit, right? So now this is a fun example you can try out. You can just pause the video here. So can you look at the cycle graph at the lift of a smaller graph? And the answer is yes, you can. So if you take a graph on 3 elements, and now let's say I'm just doing a 2 lift, right? So the symmetry group on 2 elements has just either the trivial permutation or the flip. So on the edge 1, 2, and 2, 3, I have the trivial permutation, whereas on the third edge, I have a flip. And I have 2 copies of each vertex, and in just one place, I have flipped the matchings, and in the other 2, I just have the trivial. So now it's easy to see that this forms the cycle graph. All right. So let's see why this lifting is a nice operation. So the first thing is that we can very explicitly characterize the spectrum of the lifted graph G of S in terms of the signing S. And this is very useful because at the end of the day, we need to bound the eigenvalues, of the graph. Moreover, it preserves degree, and therefore you can build a tower or a sequence of lifts, and which is why it is an often used tool in constructions of expanders. You can start with the base graph and build repeated lifts. Moreover, if H is abelian, then H acts on this. So H is a subgroup of the symmetric group of the automorphism group of G of S, and H acts in the natural way where it permutes the L copies of a certain vertex. Right? So for each vertex you have L copies, and H acts as a permutation of those. And this is very useful for us because we want to construct such graphs. And roughly speaking, we'll get into the details of this. If your base graph is good enough, and if you put the signing uniformly at random. So for example, in the two lift case, in the example we saw earlier, if I just pick the S of an edge to be plus or minus 1 with equal probability, then the lifted graph is known to be an expander with high probability. Right? And the challenge here is to de-randomize this, or in other words, to construct a finding in a deterministic fashion. All right. So let's look at a quick history of lifting. So like I mentioned, it was introduced by Pedro and Venial, and they de-randomized the two lifts. So they showed an existential result, and they de-randomized it for two lifts using techniques, discrepancy-based techniques. They essentially gave a converse of the expander mixing lemma, and that allowed them to obtain a bound of square root d up to polylog factors. Now, this was extended recently by Agrawal, Chandrasekharan, Kolla, and Madan to ZL lifts for L going all the way to 2 to the n, roughly. And they also improved the spectral gap, the spectral guarantee. However, it's an existential result. It's not an explicit construction. On the other hand, Marcus, Spielmann, and Srivastava came up with the breakthrough work, which introduced the technique of interlacing polynomials, and they gave they exhibited the existence of a two lift, which preserves the Ramanujan power. Right, so there's no loss here, so you get the optimum expanders. Another set of work by Mohanty, O'Donnell, and Paredes uses the trace bar method, and they also obtain two lifts, and they use it to construct graphs, expanding graphs for every degree using this technique, and they obtain an almost Ramanujan power. So for every epsilon, you can get an expanding family with the eigenvalue bounded by 2 square root d minus 1 plus epsilon. Right. Okay. So what do we aim to achieve here? So as you have seen, right, a lot of the work with two lifts, whereas the existential result of ACKM shows that there are good signings even when you take L as large as 2 to the n over dq, right? And they show that, and they also give a negative result, which says that beyond 2 to the nd, you cannot hope for any expansion if your group is abelian. So now our task is to construct such abelian lifts when L is in the range from 3 to this upper bound of 2 to the nd, right? So in particular, can we construct it for the cyclic group? Because this would de-randomize the result of PK, as I had alluded to earlier, right? And that's more or less what we do. So for any d, a large enough n, and a nicely growing function L of n, we have an explicit family of d-regular expanding graphs such that each graph Gn is a ZL lift of some base graph. And note here that we can generalize this result from ZL to any transitive abelian group. Transitivity is necessary because otherwise the group would be disconnected, the graph would be disconnected, and you cannot hope for expansion. So this essentially covers all abelian groups. And the niceness of the function is the function should lie in this green region. So starting from 2, we can lift all the way to 2 to the n to the c, where c is some fixed constant. And we can also lift when L is exactly exponential. So it's 2 to the Cn for any C, right? Note that we actually achieve all the way to the bound by ACKM, while their existential result holds for a slightly smaller range. So this is the key result. And this is explicit again in the sense that we can output the graph in polynomial time. And to put this back into perspective, we look at our result as like a union of two results. So in the exponential regime, when your L is actually some fixed exponential in n, then we can think of this as a generalization of the work of bilineal. And in fact, we use their key lemma, the converse of expander mixing lemma, which gives us a bound very similar to this. Right? And on the other hand, we can also look at it as a de-randomization of the result of ACKM. So what we do is we give a simpler proof of their result with a slightly weaker parameters using the lemma from bilineal, and we de-randomize. On the other hand, in the other regime, the slightly smaller lift regime, that can be thought of as a generalization of the work of MOP, because here we use similar strategy, like we use the trace bar method, and we are able to get the almost Ramanujan bounds for L that is as large as 2 to the n to the f, where f is some function of epsilon, right? Whereas if you want to lift all the way to a fixed constant, to an absolute constant, then we lose in parameters and get a bound of epsilon d, but which is good enough, still good enough to get expanders. All right. And let's recall that in the work of Panteleev and Khalachev that I alluded to earlier, given a deregular expanding graph on NL vertices, if the graph is a lift of a graph, or in general, if it has this symmetry of ZL, then you can construct a good quasi-cyclic code, linear code with circle in size n, and a quantum code with the parameters, with these parameters where NL is the block length, N is the rate, and L is the distance. This is why we want L to be as large as possible as a function of N, because that controls how good the code is in terms of the distance. Right. So as a corollary, we have explicit polynomial time constructions of good quasi-cyclic LDPC codes. So quasi-cyclic codes are like an approximation of the cyclic codes where you allow more than one orbits of the cycle, right? So here you have roughly log n orbits, and these are good quasi-cyclic codes. On the other hand, we do not know about the existence of good cyclic codes. So this is in itself a very interesting result. We also get quantum LDPC codes with almost linear distance, and these are explicit. The work of Panteleev Khalachev also gives these codes, but that's a randomized construction where each signing is where you again construct lifted graphs, but you do it randomly. So the sign of each graph is picked uniformly at random. And using their balancing trick, we can get LDPC codes with distance n to the 1 minus alpha. So for any alpha between 0 and 1, you get distance n to the 1 minus alpha and dimension n to the alpha. So now I would like to briefly mention the key technical contribution, but I'll not go into the details, is that of a better count of a certain object called hikes. So the trace bar method is a fairly common method, and a variation of this was used initially by Friedman in his groundbreaking result, which was simplified by Bordanov recently and used by MOP. So let's quickly define hikes as singleton-free non-backtracking blocks. I'm going to explain this shortly. And what the method essentially gives you is a reduction from computing a spectral quantity or bounding a spectral quantity in terms of counting certain objects, right? So it says that the maximum maximum eigenvalue of this adjacency matrix can be bounded by counting hikes of length 2k over this graph. Here B stands for the non-backtracking walk matrix, but we won't get into the details of that. So let's see what a hike is, right? So a hike is a singleton-free non-backtracking walk. So at each step, you cannot backtrack the edge you've come from. And moreover, no edge is traversed exactly once. So either it's traversed at least twice or it's never traversed. So for example, on this graph, the sequence of steps. So you start from this vertex and then you have the following sequence of steps. And you can verify that this is indeed a closed walk where each edge is either traversed twice or there's this edge which is never traversed. So it's a singleton-free, non-backtracking walk. And the goal is to count all such walks on a certain base graph. Now, if your graph is irregular, then there's a trivial way to count it, which is d minus 1 to the 2k, because at each step, you have d minus 1 options. So except for the first step, for every other step, you cannot backtrack, so you have d minus 1 potential neighbors. So you get this count, and once you plug this in here, you notice that you get an eigenvalue bound of order of d, right? Which is trivial because we've seen that lambda g is at most d. On the other hand, an ideal count would be of d minus 1 to the k, because that would give you a close to Ramanujan bound. It will give you 2 square root d minus 1. So now the goal is to get an efficient count as close to d minus 1 to the k as possible. And note that here this method works for any k. However, for multiple reasons, there are certain constraints. So the key controlling parameter is the size L, right? So how much of the lift you want dictates more or less how long you need to walk, right? Or how long of a walk you need to compute the hikes for. So in MOP's work, they focus on 2 lifts. So it suffices to bound walks of length log n. And for such length walks, they give a optimal count. Whereas we would like to lift much larger than 2 lifts. So we extend the bound to n to the delta, where delta is a function of epsilon and d. And if you're okay with the weaker bound, we can get it all the way to a fixed polynomial in n. Right? These are much longer walks. And we do this by counting in a very different manner. So let's define the hike graph to be a subgraph of the graph, of the base graph, which is traversed by the hike, right? So this is the subgraph that you see on your walk. And we're going to count hikes by dividing it into 2 steps. So first we count all possible hike graphs. And then for each hike graph, we're going to count the number of hikes that can correspond to such a graph. The second step is comparatively easier. For the first, we count all hike graphs by encoding a DFS traversal, because once you have a DFS traversal, you can compute the graph uniquely. And there are 2 encodings that we give. So a simpler one is to just store at each step whether it's a backtracking step or a recursive step. So for a backtracking step, you do not need any more data. Whereas for a recursive step, you need which of your d neighbors you would like to recurse to, or rather d minus 1, since it's non-backtracking, right? Whereas when k is not too large, so it is n to the delta for this function of epsilon, you have that the hike graph is sparse, right? And each vertex, so there are a lot of vertex with degree exactly 2. So for these vertices, you have to recurse. You cannot backtrack on such vertices. And using this observation, you can compress the above encoding further. So using this kind of a compression lets us recover the almost Ramanujan bound. Right? And then you can count the number of hikes corresponding to a given graph. So yeah, this is a vague intuition of what the ingredient of the key counting lemma is. And of course, there are a bunch of pseudo randomness tools and others that we use, but those are relatively more standard. So let's conclude. So the summary is that we give explicit constructions of lifted graphs of H, L lifted graphs for every abelian group H, transitive abelian group H, and a large range of lift sizes L. The key method of analysis is the trace power method, and to do so, it utilizes a very careful count of the special walks called hikes on a suitably nice base graph, which has a lot of nice properties, including large girth, or rather a large bicycle-free radius. And as an application, we can use such graphs to get new explicit LDPC codes. So this is a de-randomized sum, the result of Panteleev-Karachev, and we get classical quasi-cyclic LDPC codes and quantum LDPC codes. And this work opens a lot of open problems. So you could, first thing would be to extend this almost Ramanujan bound all the way to 2 to the n, right? So we have this almost Ramanujan bound only for a certain regime, and it would be nice to push it all the way. Or even like the first step would be to get expanders in the red regime, for which we don't have any guarantees yet. Moreover, we use a bunch of different encodings and different techniques in these 3 different regimes, and it would be nice to have a uniform proof, a very unified way to do these lifts, to do the analysis. And the notion of strongly explicitness, right? So as I mentioned, our notion of explicitness isn't the strongest one because we take polynomial time in the size of the graph, whereas there are stronger notions. So is this, can we make this strongly explicit? Because there are some applications where that is really useful. Right? And then it would be nice to generalize this to some families of non-abelian groups. So for example, the breakthrough work I mentioned initially used a non-abelian group PSL2FQ, but it managed to do that using the already existing graphs of Lubotsky, Phillips, and Sarnak, and some variants of those. So it would be very nice to have these for newer families, especially the families not covered by the work of Althusser and Savin, and to see if they can lead to nice applications, even possibly outside of coding theory. Right. So thank you so much for listening to the talk. It'll be very nice to have feedback, and I'll be very happy to answer questions. Please write to me at my email. Also, Fernando has given a very nice talk at IAS, which is much longer. So it covers the basics and goes into a lot of context. So please check it out on YouTube if you have the time and are interested. Thank you so much.